Good morning, I'm Manuel Sarzo, and in this video about the Unit 7 analysis of variance, I'm going to talk about two factors with interaction. And I'm going to use the following example. So let's imagine that we have one pharmaceutical company that wants to improve the yield of a fermentation process, which we will call the variable Y. So for that purpose, we run an experimental design with two factors at two levels. And this is the factors that the company chooses. The concentration of nitrogen, which is tested at level 40 and 50. Then the type of raw material, which can be type A or type B. And also, this is the experimental matrix. So we have the two types of concentration, the two types of raw material. Then we have that 40A has been tested twice, and the same for every combination. So we have four treatments. So the four combinations of the two factors, everyone has been tested twice. So we have 8 trials. So this is the result for every one of the trials obtained experimentally. And then the target of this experiment is to determine what is the concentration and type of raw material that the company should choose to maximize the yield. Well, good. So if we make the average of the pairs of the replicates, okay, we can see that the maximum value corresponds to this one. So when we work with concentration 50 and raw material B, on average we obtained the highest value. So does it mean that the best recommendation is to work with this condition? Well, maybe, but not necessarily. Okay, so if someone says that since the highest average value was 50, so maybe this could be the best solution, the best recommendation. But actually, this is true only if the effect of both factors or if the effect of their interaction is statistically significant. But we have to check this before getting to this recommendation. Okay, so we have to make the calculations. And once again, so these are the four values obtained with concentration 40. Okay, so these are the four values with concentration 50. So we put a value of short minus the grand mean squared, we sum, and we get the total sums. The sum of squares total. Then the average is the best prediction, and in this case we are obtaining exactly the same prediction. Well, actually this is like a theoretical example because this never happens in practice. But anyway, so if we have that case, so we make predicted value minus the grand mean squared, we sum, and we get 0. So sum of squares for concentration would be 0. And then for raw material, we have these four values, and from raw material B, these other four values. And then the best prediction is their average. Then we make a value predicted minus the grand mean squared. We sum, and then we have sum of squares for raw material. Okay, good. Then imagine that with this information, we make the ANOVA table. So we fill the information that we have. Sum of squares total, sum of squares for the two factor. So remember that by difference, we put the residual sum of squares, and then the degrees of freedom. We have 8 values minus 1, which is 7. We have 2 types of concentration and 2 types of raw material, which is 2 minus 1, 1. So by difference, we put 5. Remember that 4 was the minimum value. So we divide the sum of squares by the degree of freedom, and this is called the mean squares. Okay, and finally the F ratio. We divide 0 by the residual mean squares, which is 0. 128 divided by 72.4, which is the F ratio for the raw material. And then as this value has 1 degree of freedom in the numerator and 5 degrees of freedom in the denominator, we go to the Fisher's F distribution and find the critical value. In this case, for alpha 5%, the critical value is 6.6. And in this case, we can see that this F ratio is a frequent value of this distribution. So we don't have enough evidence to reject the hypothesis. So, which would mean that it doesn't matter to choose raw material A or B, that it doesn't matter to choose concentration one or the other. Okay, but in this case, so what would be the optimum operative conditions? It doesn't matter, as I was explaining. But the analysis is not finished until we check several things. We have to check if residuals follow a normal distribution, so we can do that, and actually we can see that this hypothesis more or less can be accomplished. And also very important, we have to check if the interaction between both factors is statistically significant. So this is something that we have not checked yet, and we have to do that. So then, graphical study of the interaction, more or less similar as the previous slides. Concentration 40, we had the 4 values. Concentration 50, we have here the 4 values. So in red, we have the values corresponding to raw material A, and in green, we have the 4 values corresponding to the raw material B. So now, do you think that this observed pattern was obtained by random? Okay. Well, it seems not, okay, because here for 40, more or less, it seems that there are no differences, but when the concentration is 50, it seems that these values are clearly separated. It seems that it was not obtained by random. It seems that when the concentration is 50, there is like a difference between the type of raw material, okay? So if we say that this pattern was obtained at random, which means that there is no interaction, or this interaction is not statistically significant, it means that the optimum conditions could be either of one. It doesn't matter to choose 40 or 50 or to choose A or B. But if we think that this pattern is not obtained by random, it means that the interaction is going to be statistically significant. And actually here we can see that the lines are not parallel. So they are clearly not parallel. So yes, it seems that we're going to obtain a significant interaction, as I'm going to explain next. Then, in that case, what is going to be the optimum condition? So we have 4 different combinations, and then this is going to be the best combination, because on average we're getting the highest yield, which is what we want to get. So now, what we have to do is to calculate the sum of squares of the interaction and to include that in the ANOVA table. So how can we do that? Well, so if we think that there is an interaction, as we have seen in the previous slide, it means that every combination produces a different value, okay? So 40A is going to be a different value with 40B, and a different value with 50A, and a different value with 50B. So these are the observed values. So what is going to be the best prediction? The best prediction is going to be, for that reason, the average of the 2 replicates that we have obtained in every one of the 4 combinations. Okay, then we have predicted value minus the grand mean squared. We sum, and then we got this. We got 416. But is that the sum of squares of the interaction? The answer is no. This sum is the sum of squares of the first factor plus the sum of squares of the second factor plus the sum of squares of the interaction. Okay. Well, quite often the interaction is represented like a product. I put like concentration, like multiplied by raw material, but actually we're not multiplying anything. It's just a way to indicate the interaction. But as before, we have obtained the sum of squares of one factor and the other. So by difference, we can compute the sum of squares of the interaction, which in this case is 288. And we can see how this probability is quite high. So now we can fill again the ANOVA table, but including the effect of the interaction. Okay, so as usually, first we have total sum of squares of one factor, the other, and the interaction. Look here that I'm representing this like a product, but just remember, this is just a way to indicate interaction. We don't multiply anything. Okay, so by difference we obtain the residual sum of squares, and then the degrees of freedom that I have explained before. It's 8 values minus 1, which is 7. So we have 2 types of concentration and 2 types of raw material. So 2 minus 1 is 1. And then important, the rule. So the degrees of freedom for the interaction is the product of the degrees of freedom for every factor. So in this case, it's the product of 1 multiplied by 1, which is 1. So 7 minus 3, we get 4. And remember, important, that 4 is the minimum value. Less than 4, we would get results which would not be reliable. So next, we divide the sum of squares by the degrees of freedom, and we get the sum of squares. The same for the interaction, the same for the residual, and then we get the F ratio. The first one is 0, then we divide 128 by the mean squares of the residual, we get the second F ratio, and then the same for the mean squares of the interaction divided by 18.5, we get the F ratio for the interaction. And then for the 3 cases, in the numerator we have 1 degree of freedom, and in the denominator we have 4 degrees of freedom. So we go to the Fisher's table for alpha 5%, and the critical value is 7.71. And in this case, we can see that the first F ratio is less, so it's like a frequent value, so we say that the simple effect of concentration is not statistically significant. Also, this is less than the critical value, which means that this value can be considered like frequent value for this distribution. So we will say that the simple effect of the raw material is not statistically significant. But for the interaction, we can see that this value is higher than the critical value. So we will say that the effect of the interaction is statistically significant, which is a very important result. Okay, so now, as the interaction between concentration and raw material is statistically significant, in this case, it means that we have to choose one of the 4 different combinations. This example is interesting because the interaction is significant, but the simple effect of both factors is not. So this is something that does not happen very often, but it may happen, okay, like in this example, although this example is theoretical. These are not real values. Well, so in order to maximize the yield of this chemical reaction, chemical fermentation, the company should choose concentration of nitrogen equal 50 and raw material of type B. Okay, so the average yield expected if the company works with those conditions will be the average of the 2 values that we have obtained in both conditions, which is 50. Okay, and then remember that these are important rules. So if a double interaction is statistically significant, both factors should always be included in the NOVA table. So it is not correct to say that we remove the simple effect to increase the values of the degree of freedom of the residual. No, not. In this case, as the interaction was significant, we have to keep in the ANOVA table both factors. And also an important issue is that the degrees of freedom for the interaction is the product of the degrees of freedom for both factors. What happens if we have factors, if we have more than 2 factors, okay? So then we can also study triple interactions, okay? So imagine that we have factor A, B, and C. So we could study the double interaction between A and B, the double interaction between B and C, and between A and C, but also the triple interaction. But actually, in practice, in most cases, the triple interaction is not statistically significant. So this is something that in this subject we will not explain in detail the calculation, although in general way, more or less, it is something equivalent. And here I finish this video about ANOVA with 2 factors with interaction.